Hello everyone, I am Ishant, a machine learning enthusiast, and today we are going to learn about a very interesting concept which is not very familiar with most of the people, but is definitely a powerful technique to be applied in solving classification problems. This concept is known as learning vector quantization. So learning vector quantization, or LVQ as we call it, is a type of artificial neural network which is also inspired by biological models of neural systems. It is based on prototype supervised learning classification algorithm. As we already know, supervised learning algorithms learn from labeled data, and basically after understanding the data, the algorithm determines which label should be given to new data by associating some specific patterns to the unlabeled new data. In the same way, LVQ trains its network through a competitive learning algorithm, which is pretty similar to self-organizing map, which I'm sure you have heard of. It is basically an unsupervised classification method. So it can also deal with the multi-class classification problems as well. So now we'll be looking at the basic architecture of this LVQ. LVQ has two layers. One is the input layer and the other one is the output layer. The architecture of the learning vector quantization with the number of classes in an input data and n number of input features for any sample is given below. Like we can take any of the architecture for consideration. Like for example, let us take the second one. We can see that there are n number of input units till xn here and m number of output units till ym here. The layers are fully interconnected with each other and have some specific weights on them. So basically the parameters which we'll be using in LVQ training process are x, which is the training vector, t, which is the class for training vector x, wi, which is the weight vector for jth output unit, and ci, which is the class associated with the jth output unit. So now I want to give you a fair idea of how LVQ works. This may seem a little bit intimate and you may not understand it in the beginning, but then slowly and gradually as we come to other examples, you will be able to understand. So let us say an input data of size m comma n, where m is number of training examples and the number of features in each example, and a label vector of size m comma n. So here basically L represents the size of this label vector. Now, first of all, we'll be initializing the weights of size n comma c from the first c number of training samples with different labels. That should be discarded from all training samples. That is a very important thing that we do in LVQ. Here, c is the number of classes. And next, we iterate over the remaining input data for each training example. It updates the winning vector, the weight vector with the shortest distance, that is the Euclidean distance from training example, is actually used in the calculation. And the weight updation rule gives us the following equation. Here, alpha is a learning rate at time t, j denotes the winning vector, I is the ith feature of training example, and k denotes the kth training example from the input data. So after we train this LVQ network, train weights are used for classifying new examples, and a new example is labeled with a class of winning vector. So next we'll be moving on to the algorithm or the workflow. So with this, I hope that you'll be able to understand the concept. So the training algorithm, the first step that we follow is basically initializing reference vectors, which can be done with three substeps. Substep one is from the given set of training vectors, we have to take the first n number of clusters and use them as weight vectors. The remaining vectors, as I told, can be used for training. The second substep is assigning the initial weight and classification randomly. And the third substep is applying k-means clustering method, which I hope that you all are aware of. So this is basically how to initialize reference vector alpha, and that is our first step. So now we'll be continuing with the following steps as shown by this arrow, and we will follow these until and unless the stopping algorithm tells us to stop. Those stopping conditions I'll be discussing a little later. For now, let us move on to our step 2, which is the calculation of square of Euclidean distance for j equal to 1 to m and I equal to 1 to n. I've mentioned the formula on the right hand side. And then we'll be obtaining the winning unit J, where Dij equal to minimum. And hence we'll be obtaining the winning unit J, where Dij is minimum. So these steps will be followed for every input vector X. Next, we'll be reducing the learning rate alpha, and hence we come to a final step. Now, as I told that I'll be telling about the stopping conditions, the two stopping conditions are maximum number of epochs reached or learning rate reduced to a negligible value. These two conditions are met and your algorithm is completed and it stops working. So these are basically the other variants, LVQ2, which can be used for maybe better accuracy. So and LVQ 2.1 and 3 as well. Here the input vector X falls in the window. If this condition is followed, then the updating formula is this. Similarly, if these conditions are followed, then these are met. And for LVQ3, if these conditions are followed, then these are the updating formulas. Now, I won't be boring you a lot with the theory and showing you rather a simple implementation, but I've decided to use a case study wherein we'll also be dealing with other concepts, and this will help us understand the concept with much more clarity. The case study on which we'll be executing this technique is called the leaf classification. Now, before we move on to the implementation, I want you to brief on like why this kind of classification is necessary. Now, if we talk about leaf classification, plants are considered to be one of the important things that plays a very essential role for all living beings existing on Earth and balances the nature. Nowadays, our whole Earth faces various environmental problems like global warming, loss of biodiversity, and a very huge environmental damage. As a result, some very rare plants are on the verge of extinction. So it becomes very necessary to identify and preserve the identity, features, and useful properties of these plants. Knowledge of rare leaves used for medicine and other plants is very critical in future and useful to all kinds of people like researchers, farmers, botanists, and students. Leaf identification and classification plays a vital role for plant species recognition, and in fact, in recent years, most of the researchers have dedicated their work on leaf characterization. Leaf shape, you all must know, is the major parameter to classify plants. So this is the basic of what we'll be doing in this project, and now I'll be showing you the implementation. So before that, let me show you the data set. So this is the leaf classification data set, also called the Swedish leaf. And it consists of, you can see the various characteristics of the leaves like roundness, perimeter, compactness, eccentricity, aspect ratio, rectangularity, and so on. And it consists of a huge amount of data. Like there are around 975 different kinds of leaves, which we'll be taking into consideration for our project. So now I'll be sharing with you the code for our project. So this is basically the leaf classification with learning vector quantization. First of all, we'll be preparing the data. So this is a very simple step. You all know that we use NumPy, Pandas, Matplotlib, and Seaborn libraries for data visualization and analysis. So first import them, and then sklearn is another important library which we'll be using for today. With this we can use various important functionalities like train test split, power transformer, min max scaler, standard scaler, PCA. PCA you all know is principal component analysis, and hence finally we'll be calculating the accuracy score. So first I have just read the first 5 rows of our huge data set. So it consists of the information on various parameters, as you can see. Next, I have calculated the size of the data set, as I told, 975 types of leaves with 32 features. So here iLog I have basically used as we will be like focusing on one specific kind of data of a leaf, and we read that data into this data variable and define the label for it. And then we show the histogram for that specific kind of leaf. So here are a lot of histograms, as you can see. So basically, after viewing these histograms of each feature, it can be seen that there are several features whose distribution is still not close to the normal distribution. For example, kurtosis. Here you can see it is far away from normal distribution, but for others, you can see it is still pretty close to normal distribution. So because of this, now we'll be checking its skewness. Skewness is basically your degree of distortion in your normal distribution. So basically it is used so that we can calculate the amount of skewness in the data. Here there's a variable p. If the value of p is less than 0.05 in the training data set, then we can say that it has significant skewness. So here you can see that roundness, and then let us see a few more. Here mean underscore r, these have values less than 0.05. So these two or maybe more have significant skewness. Next, before moving on, I would like to explain skewness a little bit in a better way. So basically, you can see that it is a degree of asymmetry of a distribution. If the frequency curve of a distribution has a tail that extends more to the right, then it is said to be right skewed or positive, as you can see here. Or otherwise, in the contrary, it will be called the left skewed or negative. So skewness is basically the third moment about the mean, and the normal distribution generally has a skewness of 0, or should have a skewness of 0 for a better accuracy. So you can see that some of the features have high skewness value, so that is what we need to work on. Next, we will be calculating the attribute correlation. So, for this, basically we use a test called the Pearson product moment test. It is one of the several types of correlation tests used to determine the degree of closeness of the relation between two variables on an interval or ratio scale. So the range of the correlation coefficients ranging from -1 to 0 and 1 can be conducted that the closer the value to 1 or -1 is, the closer the relationship is, whereas the closer to 0, the relationship is more weaker. So here I have given various kinds of Pearson product moment correlation coefficient that may exist. These are the various conditions. So based on these, on that table and these figures, we can explain that if the value is 0, then there's no relationship at all. 1 means perfect relationship. Now between 0 to 0.2 is very low or very weak. And then similarly low or weak. For this, it is quite large or strong, large or strong. And around this is also pretty large or strong. So now we'll move on to the pre-processing. So here, first we'll be checking whether we have any missing values or not. This is for improving the accuracy. So you can see that all the values are 0, so we don't have any missing values. Next is viewing the distribution of the value. So basically, here we'll be using the simple functionality value underscore counts, and hence we can see the data is given below. Now next, drop feature. Drop feature is basically used to exclude any unnecessary feature that we don't want to include for a project. For example, HU underscore 4, 5, 6, 7. I don't require these. So I'll simply drop it. And now this is our index. So these are the basic features which we'll be working on. So now we'll speak about normalization. Normalization, you all have studied in statistics. Basically, the how to calculate min-max normalization. This is the basic formula. The standard normalization, which is the z-score calculated from x minus mean divided by standard deviation. And similarly, we'll be using the power transformer, this function, in order to calculate the various histograms and view their normalizations using that exact formula. So now from here on, we will begin with the more important thing, that is the LVQ basic concept. So first we'll begin by splitting the data set into training sets of X, testing of X, training of Y, testing of Y. And hence we will be now calculating the input and the output neurons, as I discussed in the diagram earlier in the presentation. Let me show you. Here, these n number of inputs and m number of outputs. Similarly, these are the data which we'll be playing with today. So now this is the main classification algorithm which we'll be using, the LVQ. So we have defined the LVQ. Here you can see that the details have been given for each and every variable, what it represents, like size input, size output, max epoch, alpha, threshold, and version. Version is basically, like I told you, we can use LVQ 2, 2.13 as well. So that is basically for that. So here we take in the weight. LVQ network weight after training process, which returns the weight value. And here we will be working on the network training process. It is basically a matrix containing the training data, and the train target is the array containing the labels of the training data. Hence, the weights and labels of the weight will be written. So here we define the epochs to 0, iteration to 0. So as I talked about the basic stopping algorithm towards the end, where epoch should be less than or equal to self.max epoch. Once this condition isn't fulfilled, then we'll come out of the loop and end the process. So that is basically how we go about. And here we increase the number of iterations. More the iterations, better the accuracy actually. So here we will be carrying out the process of LVQ1 first. So as I discussed in the formula here, for LVQ, these are the updating formulas which we'll be using, and these are the conditions that should be met. So I have simply read it into the variables, and you can see that I've used those. Similarly, for the second one, these are the equations which we'll be using, these two. And these are the if-else condition which we'll be using here for these two conditions and these. Then for LVQ3 and 2.1, in the similar way, I have just read the formulas, and these are the formulas on which our LVQ will basically be calculated. So finally, we test our data in the network testing process. So param test data is the matrix containing the test data, and similarly, weight class is a tuple containing pair of weights and their labels. Hence, we will be predicting the value of the label class. So here is basically the variables which will give the output. And this is finally where we train our data for LVQ1. So here you can see in the data given below, it is basically printing the weight and the size of the weight, or weight size, whatever you want to call it. And so this is the data which we have come across from the huge data set that we were using. And finally, after testing these labels, we come up with an accuracy of 0.928327, which is pretty decent actually. Next is LVQ2. Similar process we will be using, and similarly we will be reading this weights and data. And here also the accuracy is pretty same. So we can say LVQ1 and 2 are pretty good for carrying out the processes. Now we'll be using LVQ 2.1. So after training and testing in the similar way, the accuracy has gone very down. It is 0.075, which is actually very poor, just 7.5%. So this is not a very good actually approach to go about for this leaf classification. So we will just skip it out. LVQ3, similarly, we will be carrying out the training and testing. And this also has a pretty good accuracy, but not as good as LVQ1. It is a slightly less, like 92.4% accuracy. So we can come to the conclusion that the LVQ1 and 2 are the best for providing a leaf classification. And that is how we basically perform a learning vector quantization. So with this, we come to the end of our presentation and my implementation. Hope you understood the concepts. Thank you.